A blindsight prosthesis represents a cutting-edge approach to restoring functional vision in individuals who have suffered damage to the primary visual cortex, V1, the brain region responsible for processing visual information. This damage, often caused by stroke, trauma, or tumors, results in cortical blindness, where the eyes function normally, but the brain cannot interpret the signals. The core concept behind a blindsight prosthesis is to bypass the damaged V1 and directly stimulate other brain areas to induce visual perceptions. Here's a deeper look into the technology and its implications. Mechanism of action. Bypassing the V1. Traditional visual processing involves light entering the eyes, being converted into electrical signals, and traveling through the optic nerve to the V1. Damage to the V1 disrupts this flow, leading to blindness. Blindsight prostheses aim to circumvent this disruption by directly stimulating other brain regions, such as the lateral geniculate nucleus, LGN, or higher-level visual areas, with electrical or optical signals. Stimulation techniques. Electrical stimulation. This involves implanting microelectrode arrays into the target brain regions. These electrodes deliver electrical pulses that stimulate neurons, inducing artificial visual sensations. Optical stimulation. This newer technique uses light to stimulate light-sensitive proteins, optogenetics, that have been introduced into neurons. This allows for more precise and targeted stimulation. Signal processing and interpretation. A camera captures visual information and translates it into a pattern of electrical or optical signals. Complex algorithms are used to process these signals and determine the appropriate stimulation patterns. The brain then learns to interpret these artificial signals as visual perceptions. This learning process is crucial for the prosthesis to be effective. Challenges and considerations. Resolution and detail. Early blindsight prostheses are expected to produce low-resolution vision with limited detail and color perception. Improving the resolution and fidelity of the artificial vision is a major challenge. Brain plasticity. The brain's ability to adapt and learn is essential for the success of these prostheses. However, the extent of this plasticity varies among individuals, and the learning process can be time-consuming. Long-term stability and biocompatibility. Ensuring the long-term stability and biocompatibility of implanted devices is crucial to prevent tissue damage and device failure. The long-term effects of electrical or optical stimulation is still being researched. Ethical considerations. As with any brain-computer interface technology, ethical considerations regarding privacy, security, and potential unintended consequences must be addressed. Potential benefits. Improved mobility and navigation. Even low-resolution vision can significantly improve an individual's ability to navigate their environment and avoid obstacles. Object recognition and identification. Blindsight prostheses can enable individuals to recognize and identify objects, enhancing their independence and quality of life. Enhanced awareness and interaction. Restoring a sense of visual awareness can improve social interaction and emotional well-being. Blindsight prostheses hold immense promise for restoring functional vision in individuals with cortical blindness. While significant challenges remain, ongoing research and technological advancements are paving the way for a future where these devices can provide meaningful visual experiences and improve the lives of countless individuals. Sources and related content.